Yes,
Okay,
yes.
thank you very much. So hi everyone, today I would like to introduce my research topic, learning deep net for gravitational dynamics with unknown disturbance through physical knowledge distillation. For the traditional robots in the industry, people use high-gain control to indoor robot with the ability of dealing with the uncertainty of the external environment and the internal dynamics. However, this type of the control performs poorly when the robot needs to interact with the environment. For example, high-gain control cannot be applied to the scenario where humans closely work with the robots. Recently, model-based force control become more and more popular for the modern robots. Here we give 4 examples of the model-based control. The first one is a compliance control. It creates a springy force when the position of the robot deviates from the desired trajectory while keep the robot compliance using the low-gain control. The second one is the impedance control. It can change the inertia, damping, and compliance effects of the robot system. The third one is a feed-forward gravity compensation. It compensates the gravity in the robot system, making the robot feel weightless. The last one is the hybrid force control. It incorporates the environment constraint in the control. These methods of the model-based force control require accurate dynamic model to achieve good performance. Conventionally, dynamic model can be derived by the physics law analytically. Such physics-based analytical model parameterized by the kinematic dynamics properties of the robot, such as the mass, length of links, the center of mass, etc., are able to describe the global mapping over the entire state space of the robot system. However, analytical solution cannot easily adapt to the high system disturbance caused by the unmodeled dynamics, such as internal compliance, cables, and so on, due to the fixed basis function. In such a case, extensive engineering efforts are required to further model the disturbance for specific systems, especially for the complex disturbance. Alternatively, model-free approach using the machine learning techniques to approximate robot dynamics can overcome the limitation of the physics-based model. These methods, known as the learning from scratch, did not require any prior physics knowledge. Furthermore, learn from scratch was potentially able to capture the unknown nonlinearity of the system disturbance due to their higher model capacity compared to the physics-based approach. However, achieving high performance over the entire state space of the robot system using the learn from scratch approach for the high-dose system still remain challenging. Sampling data using the learn from scratch approach was required to cover the majority of the state space with adequate density. This requirement was hard to reach for the high-dose system, since the sampling complexity exponentially increased with the dimensionality of the state space. In practice, the sampling problem prevents the practitioner from applying the learn from scratch approach to high-dose robots, considering the expense of the data generation. For example, the mechanical maintenance, long operational time. To enjoy the merits from the physics-based and the learn from scratch approach, researchers attempt to explore hybrid approach by combining these methods. One thread was error learning frameworks, where the error of the physics-based model was learned by the machine learning models. Although the error learning frameworks enhance the model capacity compared to the pure physics-based approach for adapting to the high disturbance system, they suffer from the low data efficiency similar to that of the standard learn from scratch approach, since the error over the entire state space were required to learn from scratch without any prior. Therefore, they did not solve the problem of the sampling complexity fundamentally due to their learn from scratch learning fashion. Another thread of the hybrid approach was learning the system dynamics with the estimator encoded by the prior knowledge of the physics inference. Dynamic knowledge, such as the Newton-Euler inference and the Euler-Lagrange inference, was encoded into the topology of the neural networks. This approach shows higher data efficiency compared to the learn from scratch approach. However, the ability to adapt to unknown disturbance remained poor, since the model capacity of the physics encoded approximator was drastically bounded by the pre-encoded physics prior. As a result, further engineering efforts of the model disturbance were required to minimize the model bias caused by the unmodeled dynamics, which can hardly alleviate the engineering burden compared to those of the physics-based approach. In this paper, we propose a data efficient, disturbance adapting hybrid approach using the knowledge fusion techniques, knowledge distillation. The student feed-forward neural network is learned from the knowledge of an existing physics-based teacher model and the metadata for the learning one of the classical component of the dynamics, gravitational dynamics in the Haidorff system. The learned model is further applied to the feed-forward gravity compensation control for evaluating its performance. For our approach, input-output signal was preprocessed by the trigonometric representation and input-output normalization. Traditionally, John angle is represented in the minimal representation. However, the minimal representation cannot guarantee the continuity of the John space due to the singularity of the representation in the neighborhood of the 0 and 2 pi for the John angle in the case of the revolute John, which might lead to unstable performance. To overcome the limitation, we use a non-minimum representation. The John angle are transformed by the trigonometric functions. As for the input-output normalization, we use zero-score normalization. In practice, performance of a neural network can be improved by the normalization methods to reduce the risk of getting stuck into the poor local minima. Furthermore, normalization contributes to preventing overfit for the Johns with the larger outputs in the system. Since the learn from scratch approach is limited by the problem of the sampling complexity for the Haidorff system, we propose a high data efficiency method using knowledge distillation to learn from the feed-forward neural network efficiently. Knowledge distillation was originally proposed for solving the model compression problem for the classification in the computer vision. It's widely used in the AI community due to its high data efficiency in inheriting the knowledge, such as the generalization from the larger cumbersome model, as well as learning from the new data. Compared with the neural network-based teacher model in the original version, we use the state-of-art physics-based model in our previous work as the teacher model called the physics teacher model. In this paper, we applied neural network in the feed-forward gravity compensation control to compensate both the gravity and disturbance. Inside the controller, we have 4 layers. The first layer is trigonometric transform layers, followed by the input norm as the second layer, feed-forward fully connected neural network as the third layer, and the output norm as the last layer. We designed the experiment to validate the effectiveness of our methods based on our previous work. The evaluation was carried out on the test bench consisting of the master tool manipulators of a Da Vinci research kit. We show the result of the experiments in both simulation and real hardware. We designed the simulation experiment to quantify the data saving effects. The physics teacher model were obtained by adding high noises and low noises to the parameter of the physics-based model, comparing the case of the weak teachers and strong teachers, respectively. Our approach outperformed learn from scratch when learning data was sparse. In the case of the high bias physics teacher model, the physics-based model suffered from the inaccuracy of the parameter estimation, leading to a poor performance. Notably, our method improved the performance with increasing learning data compared to the physics-based model, while it achieved similar performance compared to learn from scratch approach when the learning data was rich. In the offline test of our real robot experiment, we test the model accuracy in the 300 random configuration. In the experiment result, we found that the input-output normalization can drastically improve the performance. In addition, our model has the lowest error compared to the physics-based model and the learn from scratch neural networks. We designed an online drift test based on our previous works to evaluate the performance of the gravity compensation controller. We test the robot at the 400 testing point with random configuration and direction with the John limits. For each test, we first move the robot to the testing point using PID controller and subsequently switch to the evaluate controller for around 2 seconds. Table show that the result of the 3 robots in the online test. Our approach reduced around 75% of the mean of the average drifts for 3 robots compared to the learn from scratch. The performance of our approach was slightly inferior to that of the state-of-art physics teacher model in terms of the means and standard deviation of the average John drifts. However, their performance was comparable since the maximum mean of the drifts for 3 robots were in the same scale compared to that of the learn from scratch. Finally, we show that our gravity compensation controller, learning with the physical knowledge distillation, can compensate gravity and disturbance effect of the robot in most of the usable workspace. To demonstrate the result, the robot was manually moved to the random configurations and released when it was stable. We can see that the drift was very small, indicating the good performance. So thanks for listening.